Okay, so now let's start it. Yeah, so dear students, welcome to your channel, that is AP Physics. Okay, so now we'll be starting our class. Okay, I hope I'm audible. Let me check it online. So dear students, welcome to your channel, that is AP Physics. Okay, now we'll be starting our class. Okay, I think everything is online. If anybody has sent any comment, let me check it there. Okay. I think so. Please, but anybody who send any comment, let me check it there. Okay. So, dear viewers, due to your comments, the previous video has been deleted because there was some technical issues in that video. Okay. So now what I'll be doing is this, I'll be starting it again for you. Okay. So without wasting time, let's start. Okay. So at first, we'll be seeing gravitational potential. Okay. Okay, let's understand this. What is this term gravitational potential? Till now, we have studied gravitational intensity. Okay, we have studied universal law of gravitation. After universal law of gravitation, we have studied gravitational intensity. Now we'll be studying gravitational potential. Let's understand this. Suppose you are having a capital mass m here, okay, and you're having m naught mass at position B, and your capital M mass is here. It's in static condition. When I say it's in static condition, I basically mean it doesn't move. It's not moving. Okay, it's not moving. So now if I bring this m naught mass from A position, from B position to A position like this, what are you going to feel in this? It's very easy. Suppose you're having m naught mass from B position, you're bringing it at A position. So as per the Newton's universal law of gravitation, you'll feel that you'll have to do some work for against a force which is resisting force. You'll feel that this capital M will attract this. Of course, this M naught will also attract this capital M, but due to its mass is very big, nothing will happen. But you will always feel during the journey between B and A positions, you will always feel that there is some force which is externally attracting this M naught, and you have to apply consistently. Consistently, you have to apply a force against that attractive force. Okay. So we'll say you will have to do a work to move this from B to A. Okay. And students, this work done from B to A divided by this M naught. See, this is a crisp course, so you'll be able to understand all the things properly and then apply the numericals. So work done from B to A upon M naught. This is potential difference of these two positions, V minus V. This is a very familiar expression. When you have studied work energy power, you must have encountered this. Okay, so please note it down. So we'll say work done from B to A upon M naught is potential difference of these two positions. It's well defined already. Okay, please note it down. But our topic is gravitational potential. When I say gravitational potential, it means at a particular position, what's the answer is. That we'll find in the next. Just note it down. Okay. So now I'm erasing this. If there is any technical issue, please tell. Now, now let us assume that this B position is infinity and this is some R. So the mass is same, okay? And R means it's R distance from this. Now if you're bringing M naught mass from infinity to R position, okay? So we'll say at this, at a particular any R, we'll say gravitational potential is what? If it's asked from you, what's the gravitational potential is? So you will say this is equals to G. Okay. Before finding the generalized expression of this, we'll see first generalized derivation. Okay. So you know work done from infinity to any r random position upon m naught as per the previous expression was equals to what? It's equals to v r minus v infinity. Now we know this thing that potential, whether it's electrostatic potential or gravitational potential, is to be treated at infinity as equals to what? It's zero. Okay. So we'll treat this as zero. Okay. So here we'll say VR upon M0. This is our expression. Remember this. Okay. So now after finding this, we'll solve a numerical based on this class illustration. Please note it down. Okay. I hope you have noted these crisp notes. Now we'll be solving a numerical based on this. Okay. Now let's see. Okay. So the question is, yeah. So this is a class illustration in front of you. It says if potential at point P. So in the space, there is some point P. The potential at that point is well defined as 100 joules per kg. Why 100 joules per kg? Because you know it's work done by mass. So work done according to work energy power is always in joules and mass in SI unit is kg. So joule per kg. And 20 joules of work is done in moving 5 kg mass from P to Q. Again, very easy. You have to find the potential at Q. Please note it down and solve it. Okay, so I hope you have solved this. Let's check. So we know the equation that work done. Suppose the particle moves from P to Q. So I'll say VQP upon mass of the particle is equals to VP minus VQ. This was the first generalized expression which we have already seen, isn't it? So we'll say VQP. Very nice. VQP is the work done. Okay. So we have 20 joules given already. So I'll substitute here 20 joules and the mass is given to us as 5 kg. And VPQ. So we have V, we don't know what's a VQ, but we have this value that is 100 joules per kg. Okay. So now let us see the answer. 20 upon 500 minus VQ. So here it's 4, it's 100 plus 4. Okay. Hold on one second, hold on one second, hold on. We need to find it VQ, no? So we'll say VQ minus, it's from P to Q. If it's P to Q, we have to change some things here. Apologies. P to Q. So it's VQ, because whatever the wordings you are writing here, it must be reversed. So it's PQ, so it will be VQP. Okay. So here we have VQ, we don't know VP, we already knew it, that is 100. So from here we get 100 plus 4 and the answer is VQ is 104 joules per kg is our required answer. Please note it down. It's very easy. I hope, dear students, you are able to solve it. Okay. So now next we'll progress towards gravitational potential due to point mass. Now we'll see gravitational potential due to point mass. Gravitational potential due to point mass. Let's check it out. So suppose you're having capital mass m here, like this. Okay. And from r distance to this mass, if you are asked that at this random r, what's the expression of gravitational potential of this point mass? Treat it like to be like a point mass. Okay. So how you'll answer it? It's very easy. First of all, let's check what's the intensity here. So gravitational field intensity at any r is given by this expression gm by r squared. Now, to find this or to prove this, I mean, let me tell you what to prove. Answer will be minus gm by 1. This is our potential at any r. This is potential at any r. Okay. So now the question arises how to find this. To prove this, we'll be using analogy from work energy part. Okay. You know this thing that du by dr is equals to 4. Isn't it? Du by dr is equals to 4. You can take other magnitudes. So what happens in this? The force can be changed to gravitational field intensity. Potential energy can be changed to potential. R is the same. The expression changes something as E, which will be now dV by dr. Okay. So now we'll do some substitution here and we'll try to prove this. So we'll say this goes gm by r square and dV is equals to now gm by r square dr. Just Integrate it, and you will get the answer minus Gm by R. We'll suppose it's from infinity to R. We'll suppose it's from infinity to R. Because at infinity, we know it will go to zero. And potential is V at particular R minus V at infinity. And potential at infinity is also taken as zero. So when you solve this, you'll get this expression as a direct answer. That is minus G capital M by. Some students will see if you go as by the operator sense, and this is a big thing, it's minus del upon del x I cap, minus del upon del y g cap, and minus del upon del z key cap. I have just taken a magnitude here. It's a just simple analogy to understand the things in a more convenient way and to remember this for a longer period. Okay, please note it down. So I hope you have noted it down. Let's move next. Now we know it's scalar quantity. The units you can see yourself, it's joule per kg only. Okay. Now, sometimes you've been asked not just due to point mass, but at a particular point due to random masses. Okay. System of point masses. Then what do you want to do? So, now we'll understand gravitational potential due to system of point mass. Let's understand gravitational potential due to system of point masses. Okay. So for this, suppose in a space, this is x-axis, that is y-axis, and this is z-axis. Okay. Suppose in a space, we're having a point. Let's locate a point something as this P, X, Y, Z. Okay. And in the vicinity of this point, suppose there are a lot of random masses. Okay. When I say n, it's a discrete particle system. You must mean that there are many other masses too. I mean, it can be like 5, 6, 7, 8, 9, 10, 11, 12. Infinite, no, it will not take infinite mass. Up to a certain range number, say 100, it works. Because if you take a lot of number of masses, it goes for the case of rigid body. Okay. So now let's see. Suppose this distance is something as r1, radial distance is r2, radial distance is r3, and radial distance is rn. So at this point P, having the Cartesian coordinates x, y, z, what will be the potential at this point P due to all other masses if we want to find it out? We'll say the net potential will be equals to minus the expression which we have just pointed out, R1 minus G M1 M2 upon R2 dash dash minus G Mn upon R. So this is a random expression. Okay, please note it down. Now you are having a question to solve based on this. Let's erase this. I hope you understood. Anybody having it out, please ask. Now let's check a numerical. So the case is this, three equal masses are situated at the vertices of equilateral triangle. When I say equilateral triangle, it means two things basically, which must click in your mind. The first is all the sides are equal. The second is the angles are 60 degree, 60 degree, and 60 degree. So there is a center point too. It's been asked from you in this question, you have to find the net potential. When I say potential, it means the gravitational potential. You have to find the net gravitational potential at this center point O. Please find it out. Till then, few students are giving the comments key. I mean, there's maybe any technical issue. Let me check it out there online. Net potential. Okay. So I think that this much time is enough for you to solve. Now let's see. If you see the projection of this point at the base, 100%, this distance must be by geometry and common sense, it must be a by 2. If you just analyze the things and are able to answer it, this must be a by 2, isn't it? So now this in between angle is 30 degree, because if the complete is 60, the center line, I mean the line which is joining this vertices and the center, not just this vertices mass and this center, it's about all the vertices of the equilateral triangle. And when joined by the center, all the along line or the radial line will intersect the angle or bisect this angle, if I must say. So this will be 30 degree. I'll say projection of R on the base is R cos 30 degree is equals to A1. Cos 30 is how much? It's root 3 by 2. A1. Okay. So we have R as A by root 3. Something like this. R is equals to what? R is A by root 3. Okay. So once you get the R, it's not this easy to find the net potential at the point O, center. Yeah. The question will be, see, this R is same for this vertices and for this vertices. So I'll write the net potential at the center O point is 3 times of the same expression. So 3 times of the same means minus G M by R. R is how much, dear students? It's this one. So answer will be minus 3 GM by R. R is equals to A by root 3. Minus 3 root 3 GM by A. This is your net potential. Minus 3 root 3 GM by A. Please note it down. Okay. So I think you have completed this. Now we'll see some cases. Okay. So gravitational potential gravitational potential due to ring basically at axis. Okay, let's check. Yeah, it's visible. Okay, fine. So we'll say suppose we are having a ring and a ring is having the mass m and radius is equals to r. Okay, very nice. So ring is something like this in front of me. So on the axis, if I say at x distance, there is a point P here. And if you're asked to find the potential at this point, what the expression is? We are not required to derive here. We just have to remember the formulas, the expressions, and apply the application. So it will be basically minus, remember this, minus G M upon, this is under root R square plus X square. This is your random expression. This is the potential at any point P on the axis of a ring. Now, one beautiful thing here. Suppose we need to find the potential at the center of the ring. If we take here some dm mass, as per this, the potential will be, you know it, it will be something as minus g dm integral upon distances r, isn't it? Minus gm upon small r, so small r is equals to capital R. If we integrate this, this gives us the expression minus gm by r. Easy proof. We can easily prove this. So at the center here in this expression, x goes what? X goes equals to 0. So we'll say potential at the center point, not at a particular point P, but at center is minus Gm. X0, R square root is minus Gm. So this is verified, isn't it? So at the center, we'll say potential is, if either if you find by this, else this. Answer is minus Gm upon capital R. Easiest. Please note it down. I hope you have solved. Okay. So now let's move. Okay. So now we'll see the next on the list, that is gravitational potential due to holosphere. Dear students, when I say holosphere, it means basically the mass distribution is along the periphery, isn't it? So here will be, we must understand this thing that to find the potential, there must be three cases. So case one is for less than radius, on the periphery, outside of the zone of the mass. I mean, outside of this holosphere. Okay. So here, just remember the answer. It's potential at any point inside is minus G M upon R on, no, it's this capital. Yeah, this is the result. So it's the constant result as on the periphery. On the periphery, you know, the answer is same, minus G M upon capital R, isn't it? Here, the potential outside is, you can guess the answer? Yeah. So as per the center of mass concept, we can assume all the mass of this hollow sphere is concentrated at the center. So we'll say like a particle system minus Gm upon R. So these are both same as per mathematical analysis. Okay. So now let's move next. Yeah, if you are asked to draw the graphs, I hope you get an idea. So for inside and if this it's constant, then it's inversely proportional to 1. So now let's draw the graph of this, and we'll check the next answers. Okay, let's note it down. So for the graph, if you see potential versus R radial distance, we know for R less than equals to R, it's constant potential, that is minus Gm upon R. For R greater than R, its potential is equals to minus Gm upon this. So for this, the potential is always constant, and for this, it's inversely proportional to. So the answer will be this, that is minus Gm upon capital R. And when it reaches here, R equals to R, it goes inversely proportional to this. So this is the graph, students. Okay, please note it down. It's very easy. One of the easiest graph here. Okay, so maybe there is some technical issue. We'll check after finding out for the solid spheres. Okay. Okay, let's move next. So now we'll see gravitational potential due to solid sphere. Gravitational potential due to solid sphere. The difference between hollow sphere and solid sphere is very basic. You know, the mass distribution inside or the mass density inside it's not present in hollow sphere. Solid sphere, everywhere there is mass on the periphery inside the material. Okay. So here also the three cases arises basically. So for this, anybody can analyze. You can here also apply the concept of center of mass. So you'll think like this. All the mass is supposed to be concentrated at the center. So a particle system can be applied here. So you'll say the answer goes to potential, and for this is minus Gm at any R outside the radius. It's this easy expression. For R, again the same, that is for the hollow sphere, that is V minus Gm. Now for this, what do you think? What's going to happen? See, there is a complete derivation for this, that you can take a density. You can also use something like 4 pi r square dr, find the mass density for particular radius sphere inside this sphere, and then apply the formulas. Then you're able to solve it. In electrostatics, there is more better approach for solving these kind of questions to find electrostatic potential by using the Gauss laws. We can also use the Gauss laws for the gravitation, but this is beyond the scope of the syllabus as per the IB, SL, and HN physics. Now, what you're going to do is this for this year, for this session. Now, you have to just remember the formula for this. So we'll say potential is equals to minus, of course, minus will always minus G M upon R cube, radius cube, 3 R square, radius square, minus R square, radial line square, which is inside R, upon 2. Remember this. So this formula must be remembered always that for R less than radius, potential at any point inside is equals to minus Gm upon 2R cube, 3R square minus R square. This is one of the basic formulas. Okay. Please remember this. This is very easy. Remember this, please. Okay, let us we know this thing at radius equals to at radial distance equals to radius, that is on the periphery, the potential is minus Gm upon capital R. If I'm going to insert the value R equals to R in this expression, what do you think answer will come? So this is 2R square, 2R cube, R. Answer will be same again. So this proves the expression is 100% accurate. Okay, please note it down. Now we'll see the expression for this. As we have seen for the holosphere, the graphs, we'll also see for the solid sphere. Let's watch the graphs. So let's draw the graph for. So we know the expressions. I'm just going to directly draw the graph. So initially it was static, but now for R less than R, it's minus Gm upon. Remember always 3R square minus R square. You can see it's proportional to R square, but it's negative. Then again comes the negative. And here for R equals to R, it's just minus Gm upon R that we know, but for R greater than R, it's minus Gm upon R. Here it's inversely proportional to R, here it's directly proportional to R square. Curve comes out to be this. Okay, please note it down. Please note it down, then we'll dive deep into the mathematical analysis for a relationship between gravitational potential and gravitational field intensity or gravitational intensity. Okay. Okay. So I hope you have noted down things. Let's move next. So now let's understand the relationship between gravitational potential and gravitational field intensity. Okay, this is a generalized expression for gravitational field intensity minus del V by del R. So we know electric field intensity, sorry, gravitational field intensity is basically it's in proportional to force. I mean, it's a vector quantity, but this is a scalar quantity. So this is a very interesting expression which basically connects vectors with scalars. A kind of simple connection. So if it's vector, it must be x, y, z. Okay, so we'll say here. Very simple, isn't it? So please note it down. Because now after this, you will be solving a numerical, and the numerical is this. So question is this: you are given a potential as 2 upon x cube. This is your potential given. Which potential? Gravitational potential. You have to find electric field, you have to find gravitational field intensity at x equals to 6. Please find it out. Find it out. Very easy. Let's apply directly. We are having the x term, the y term and the z term are absent. So what you're going to do is this, it's not required for you here to apply the partial derivative, just directly apply what? Derivatives. So this del upon del thing can be changed to Transformation can be applied here to D, which means infinitesimally small things. I'll say just differentiate this. So the expression can be written as that electric field intensity at x can be minus dV by dx. So we'll say minus 3 nx n minus 1. Okay. So we have the formula for y x n dy by dx. This is nx n minus 1. Let's apply this. So when I'm going to apply this, this is x minus 3. So minus 3 minus 1 is minus 4. Okay. So minus 3, 2 upon x4. 1 minus 1 already there. So it goes plus. So the answer comes up to be this is 3, this is 2, this is 6. Okay. So this is 6. So when we will answer it, let me write this thing on the top. Let me raise the upper part. So you will say E is this is equals to 6 upon x4. Okay, very easy. So just insert the x equals to 6 thing here. This is 6 raised to power 4. This will be, you'll get 1 6 cube here. 1 upon 216. This is your potential. This is your potential, and this is the right answer. Okay. Units, potential is how much? It's joule per kg because we know work done upon unit mass. Please note it down first. Please note it down fast. Let me check if there is any issue online. Please note it down fast. Let me check if there is any issue online. Okay, so I hope you have noted down all the things. Very good. Let's move next. Okay, let's move next. So after the gravitational potential, now we're going to learn gravitational potential energy. Yeah, it's a little bit changed, but no worries, it works. It works. Now we'll see gravitational potential energy. What is this gravitational potential energy? Okay. First of all, it's an energy due to configuration of the system of particles. It's an energy due to configuration of the particles, mass particles, point masses. Okay. The first point you must remember, it's energy due to configuration. Okay. Now let's understand in a more depth. Suppose these are two masses and these are situated at a distance r1. Okay. So potential energy for this is defined as ui. Let's suppose this is a configuration number one. For the configuration number two, the same masses, if I am creating a distance r2 which is greater than r1, so now we'll say this is the final potential. This is basically the final potential energy. Okay. So it's defined, you must always remember this thing, it's defined that change in potential energy, U final, the change in potential energy, that is U final minus U initial, is equals to negative of the work done by conservative forces. Okay, or you can say if I am just picking this up and doing this, so you'll say change in potential energy is equals to work done by external force, which is me, an external agent, something like this. This will be used in solving the numericals, which is just yet to come. Please note it down. So now we'll see. Now we'll see gravitational potential energy due to two particle system. Okay. Now we'll see gravitational potential energy due to two particle system. Suppose we are having two particles, M1 and M2 at infinity. M1, M2 at infinity. When I say we have two particles, M1 and M2 at infinity, it basically means they're very far away. It's just a visualization, it's just a supposition, assumption. Okay. So after this, if I'm bringing, if suppose somehow by an external force, by an external agent, it's like an octopus hand. I'm just picking this up and keeping here in a certain configuration. M1 is a certain configuration at a distance or something like this. Okay. So I picked this masters and kept here. This is a certain kind of configuration. So to generate this configuration, I have to do some work. Work done by an external agent like me. So that work done is stored in the form of potential energy, gravitational potential energy of this particle. We directly define the formula as U minus G M1 M2 distance between them. Please remember this, it's very, very important. It's very important. Please note it down. After this, as we have seen for the potential, gravitational potential, we'll see for the gravitational potential energy. due to system of masses, we'll see the gravitational potential energy. Okay, please note it down. Okay, so you can also be asked by changing the words in the exams. You can also be asked by changing the words in the exams, like find the gravitational potential energy for this system or find the gravitational interaction energy. Find gravitational interaction energy of this system. For example, we have this configuration, system of configuration of particles where M1, M2, M3 masses are like on a triangle. We can't say it's equilateral. It seems to be equilateral, but we can't just suppose it. So the distance between M1 and M2 is R12. The distance between M2 and M3 is R23. And distance between M3 and M1 is R3. You have to find the gravitational potential energy or interaction energy of the system. It's very easy. Remember, if just suppose this is not present, so you will say, what will be the gravitational potential energy of these two particles? It's very easy. Write it. It's something as for U1, 2, it's minus G M1, M2 upon R12. So now for these two, just hide this. So it will be for U23, it will be minus G M2, M3 upon R23. For these two, just hide this. So you will say U31, it will be minus G M3, M1 upon R31. Just sum up all these. We'll get the net gravitational potential energy or interaction energy. What's the mistake you can do is this and this kind of thing. Sometimes you just add the same expression twice. Don't do that. Or if you are doing this, you will do that like this twice or twice. So at the end, just divide the complete expression by half. But it's better if you apply this analogy of hiding one of the masses and then adding all of these because these are scalar quantities. As the gravitational potential is scalar, gravitational potential energy must also be what? It's a scalar quantity, but because we know it's just an energy. Okay, please note it down. Okay, dear students, we'll meet in the next session. Till then, please revise all the things. Bye bye. Take care.